In this class, I'll continue our discussion and introduce some more theoretical aspects of radiation heat transfer. In the previous class, I explained the total emissive power as the total radiation emitted from a surface per unit area per unit time in the hemispherical direction. It is also known as hemispherical emissive power. But today, I'll explain another term, monochromatic emissive power. It is the radiation energy emitted from a surface per unit area, per unit time, per unit wavelength at a particular wavelength. So the radiation emitted from a surface in all the directions, but at a particular wavelength, one particular wavelength per unit area, per unit time, per unit wavelength emitted from that surface. That will give the monochromatic emissive power. It varies with the wavelength and surface temperature. I'll explain this variation with the help of a graph. Now this graph shows the variation of monochromatic emissive power of a black body with wavelength of the emitted radiation at a constant temperature. For a real surface also, the plot will have a similar nature, but the values of monochromatic emissive power at any given wavelength and temperature will be always less than that of a black body. So the plot will be of similar nature, but always the curve will go below this. It will fall below this curve. So EB lambda, that is monochromatic emissive power, is changing with the wavelength of the emitted radiation. For any given temperature, with the wavelength, the monochromatic emissive power will change. And let us consider at a one particular wavelength lambda, corresponding value of monochromatic emissive power. Let us take it as EB lambda. That is the monochromatic emissive power. What is the unit of monochromatic emissive power? Watts per meter square micrometer. From the definition itself, it's clear. It is the, and watts means joules per second. So that is energy emitted per unit time, per meter square area, per unit wavelength. Around this wavelength, whichever wavelength you are taking, around this wavelength, for unit wavelength, how much energy is emitted from that surface per unit time, per unit area. That will give the monochromatic emissive power. So once you know the monochromatic emissive power at one particular wavelength, if you multiply by the d lambda, that is a differential wavelength around this, which will give the energy emitted from the surface of the body per unit area, per unit time from this differential wavelength range. So once you know that EB lambda, that is emissive power, monochromatic emissive power at one particular wavelength, if you multiply with the d lambda, you will get the area, this area, which will give the energy emitted per unit area per unit time. So EB lambda into d lambda will give the area of the strip, which will give the energy emitted per unit time per unit area from that surface for the differential wavelength. Now if you integrate from 0 to infinity, that will give the total emissive power. That is, you are taking all wavelengths changing from 0 to infinity. For that particular temperature, you are taking all the possible wavelengths at which the energy is emitted. So total, if you are to find out total emissive power, if you are to find out, you have to integrate from 0 to infinity. EB lambda, when you multiply with the wavelength, differential wavelength, that unit will give watts per meter square. That is energy emitted per unit time per unit area. Integrate that from 0 to infinity, which will give the total emissive power. That means you are considering all possible wavelength of emitted radiation at that particular temperature. Finally, it leads to Stephen Boltzmann law. You will get EB as sigma t to the power of 4. Max Planck distribution law. You will see what is Max Planck's distribution law. Max Planck's distribution law gives the monochromatic emissive power of a black body with the temperature and wavelength of the emitted radiation. So monochromatic emissive power of a black body, how it varies with the temperature and wavelength of the emitted radiation. This is the expression EB lambda is equal to C1 by lambda raised to 5 into E raised to C2 by lambda t minus 1, where C1 and C2 are constants. And C1 values 3.742 into 10 raised to 8 watts micrometer to the power of 4 per meter square, and C2 is equal to 1.438 into 10 raised to 4 micrometer Kelvin. So this is Max Planck's distribution law. So Max Planck has given that for a black body, how that spectral MEC power for a black body is changing with the temperature and wavelength of the emitted radiation. It is given by this expression, and it is known as Max-Planck distribution law. For a given temperature and at every wavelength of the emitted radiation, black body will have a maximum monochromatic MEC power compared to any other non-black surface or real surface. Now it shows that variation of monochromatic MEC power with the wavelength of the emitted radiation for different temperatures. So it's a different constant temperatures. Say it is 800 Kelvin, 750 Kelvin. So when the temperature decreases, the energy emitted, monochromatic MEC power is also decreasing. It will have a different curve, like with the peak shifting towards right. You can clearly see from the graph peak for this. At the higher temperature, the peak is left side. Now when the temperature decreases, the peak point is shifting towards right. So here you can see the peak is beyond around 0.5 into 10 to the minus 5 meter. Whereas this peak is less than 0.4 into 10 to the minus 5. So the peak is shifting. From these graphs, you can see that when the temperature decreases, the peak value of monochromatic MEC power is shifting towards right. That means at a lower temperature, the maximum monochromatic MEC power occurs at a higher wavelength. When the temperature decreases, the wavelength at which the monochromatic MEC power is maximum is increasing. At a higher wavelength, it is having peak value of monochromatic MEC power. Whereas higher temperature, at a lower value of lambda, it is having the peak. At lower temperature, it is having higher value of lambda, it is having a peak. So this observation you can make from the graph. Now let us see what is the Wien's displacement law. So Wien's displacement law, it is nothing but what observation we have made from the previous graph. At different temperatures, we have seen that how the monochromatic MEC power is varying. So at higher temperatures, the peak occurs at a lower wavelength, and lower temperatures, the peak is at a higher wavelength region. So he observed special feature of this graph, and he has got a relationship between the lambda and T at which the maximum monochromatic MEC power occurs. So he finally got the relationship between lambda and T as lambda into T is equal to 2897.6 micron meter Kelvin, or 2900, approximately 2900 micrometer Kelvin. So that is the relation product of lambda and T at which maximum monochromatic MEC power occurs, or peak value for this curve occurs. When the peak occurs, that product is 2897.6 micrometer Kelvin. So this is Wien's displacement law. I will explain this with the help of graph. Now this is the plot of T lambda. It is not for a black body, it's any surface, it is true. This is monochromatic MEC power, not for especially for a black body, any real surface also. So E lambda shows the monochromatic MEC power, and lambda is the wavelength. So this graph shows the variation of monochromatic MEC power for different temperatures. So I have shown the 5 different temperatures. One is T1, and then T2, T3, T4 and T5. So 5 different temperatures the plot is made, how that monochromatic MEC power is varying with the wavelength of the emitted radiations. So Wien's distribution law is especially for the peak point. So this curve is having, this black curve is having a peak here, and this red curve is having a peak here. Similarly, you have a peak points are marked. Now as per this law, the temperature and wavelength is at lambda 1 you have the peak. For the second red curve, that is at a different temperature T2, at lambda 2 you are having the peak. For this green curve T3, temperature is T3, at T3 it's plotted. So for that lambda 3 you are having the peak. And similarly you have a different lambda values, you have a peak. So lambda 1 is less and T1 is more. Here lambda 2 is more than lambda 1, but T2 is less than T1. Now the higher value into this lower value of lambda. Now this is lower value and the higher value of lambda. Now this product if you take T1 lambda 1 is equal to T2 lambda 2 is equal to T3 lambda 3 is equal to T4 lambda 4 is equal to T5 lambda 5. So that product of temperature and wavelength at which this peak occurs, that product remains constant. That is nothing but Wien's displacement law. So Wien's displacement law states that the product of temperature and wavelength at which monochromatic emissive power is maximum is a constant, and that constant is 2897.6 micrometer Kelvin. So the product of lambda and the temperature at which peak occurs is equal to 2897.6 micrometer Kelvin. This is Wien's displacement law. And we can also prove this, whatever value is given by Wien's displacement law, you can prove it by, at the peak you will have that slope of this curve 0, and we have that distribution, this distribution is as per Max Planck's distribution law. So we have that Max Planck's distribution law, and how that curve is varying, how that distribution takes place, that equation we are having. And for that equation, if you differentiate and equate to 0, you will have a slope 0 here. Max Planck's distribution law depends on two values, temperature and wavelength. But here the plot is made for constant temperature. So only lambda is varying in this case. So with respect to lambda, if you differentiate and equate to 0, you will get the peak point. That is, you get a relationship between lambda and t. So that will prove here. So this is a equation for Max Planck's distribution. Okay, the EB lambda was given by C1 by lambda raised to 5 into e raised to C2 by lambda t minus 1. I am differentiating EB lambda with the d lambda. So d by d lambda, that is differentiating this Max Planck's distribution law. I am differentiating that equation with respect to lambda, where lambda is the only variable, t is kept constant while plotting that curve. So differentiating with respect to lambda, so I have taken lambda raised to 5 to the numerator. Okay, that will go as lambda raised to minus 5. So you get d by d lambda of C1 lambda raised to minus 5 divided by e raised to C2 by lambda t minus 1. Now numerator you have lambda and denominator also lambda is there, which is a variable. Lambda is a variable here. You can differentiate this with respect to lambda by applying the quotient rule for differentiation. So first denominator into differential of the numerator. Denominator I have written differential of the numerator. Differential of the numerator will be minus 5 C1 lambda raised to minus 6. So denominator I have written differential of the numerator is minus 5 C1 lambda raised to minus 6 minus of this C1 lambda raised to minus 5. Numerator you can write as such into differential of this. Differential of this is the same e raised to C2 by lambda t will come. This is a constant that your differentiation is 0. This you should differentiate. The same quantity will come. Then you have to differentiate this with respect to lambda. Okay. So minus C2 by lambda square t. C2 by lambda t, 1 by lambda differentiation is minus 1 by lambda square. C2 and t are constant. So when you differentiate this exponent, you get minus C2 by lambda square t divided by denominator square. Denominator square is e raised to C2 by lambda t minus 1 whole square. Now that you can equal to 0 because at the peak and the slope is 0. So numerator should be equal to 0. Numerator you can equal to 0. Okay. Here again you can take that C1 lambda raised to minus 6 is there. Here also C1 lambda raised to minus 5 is there. But if you take this 1 lambda to the numerator, you will get lambda raised to minus 6. So 1 lambda I take from here. So lambda raised to minus 6. So C1 lambda raised to minus 6. I'll cancel that C1 lambda raised to minus 6. Okay. So what you get next? Minus 5. Minus 5, I'll take one term to the right hand side because it's equated to 0. I'll take the one term to the right hand side. Here you have minus of minus plus. And this minus sign goes to the right hand side, you will get plus. So C1 lambda raised to minus 6 I cancel, you will get 5 into e raised to C2 by lambda t minus 1. So it's equal to, this term get cancelled. Including 1 lambda here it's cancelled. So e raised to C2 by lambda t into C2 by lambda t. 1 lambda is only I have taken here, 1 lambda is the C2 by lambda t. Now what I do is, the whole equation I will divide by e raised to C2 by lambda t. So e raised to C2 by lambda t, if I divide, you get 1. Here 1 by e raised to C2 by lambda t. So e raised to C2 by lambda t, if I take to the numerator, you get e raised to minus C2 by lambda t is equal to, this is cancelled, C2 by lambda t. Now I will substitute C2 by lambda t as x. So you get 5 into 1 minus e raised to minus x is equal to x. This is substituted as x. C2 by lambda t is substituted as x. So you get x here 5 into 1 minus e raised to minus x. So we get x is equal to 5 into 1 minus e raised to minus x. Solving this transcendental equation by trial and error, we will get the value of x as 4.9651. So we know the substitution. C2 by lambda t is substituted as x. So C2 by lambda t is 4.9651. Now from this you get lambda t as C2 by 4.9651. Now substituting for C2 as 1.2387 into 10 raised to 4 micron meter Kelvin divided by 4.9651, you will get the lambda t as 2897.6 micron meter Kelvin. That is the value at which the product of lambda t at which the maximum monochromatic emission power occurs. Thank you for watching.